Our next speaker is Matthew Valheim, and he will talk about on the universality of linear dynamics.
Well, I'd like to thank Karin and Renal for the invitation and Renal for starting this International Society of Quantization Geometry and Dynamics. And I'd like to thank the Air Force Office of Scientific Research for supporting this work. I'm going to talk about joint work with my colleagues Philip Erthun and Eduardo Sontag on the universality of linear dynamics. So let me tell you about what universality is. A couple of basic definitions that I'll need to state the problem precisely. So a flow, just a usual flow on a set, it's just a group action of the real numbers. So a map phi satisfying the time zero map, phi zero is the identity, and the composition of the time t map and the time s map is just the time t plus s map. And I'm also going to need a notion of embeddings. So fix any non-negative integer k, or k could be infinity. And I'll take X to be a topological space if k is 0, and a CK manifold if k is at least 1. And so these are standard definitions, although I may have stated them in a slightly funny way, but they're equivalent to the standard ones. So a map H between spaces X and Y is a C0 embedding or a topological embedding if when you restrict the codomain, H is a homeomorphism onto its image. So H is in particular injective and continuous. And a CK embedding with K at least 1 uh, is such a map H where the image of H is a CK manifold, and H is a CK diffeomorphism onto its image. So the general definition of the universality problem is that a class of flows C, so some collections of flows on various spaces, is CK universal for another such class D if for any flow X, phi, and D, so phi is a flow on the space X, so any flow in D is required to admit an equivariant CK embedding into some other flow, psi on some space Y, belonging to the class C. And by that, I mean that there is a CK embedding H going from X into Y, such,
Matthew,
uh-huh.
may I ask if you have a slide with the definitions?
Um, this one.
It's not showing.
Ah,
Something
uh,
is wrong because I'm only seeing the first page.
I see. Are you seeing still only the first page?
No, now I see something, some icons.
Um, but not a slide.
No.
Okay, let me try something else. Let me try sharing my entire screen. Um,
Okay, now we're seeing it.
okay, so you never saw this slide, did you?
No.
Okay, okay, so I guess I'll go a bit fast because hopefully these ones we're familiar with, but so flow for me is just the usual flow. So I'll be denoting them by phi. Phi 0 is the identity. Phi t composed with phi s is phi t plus s. Um, so I'll be considering uh, non-negative integers or infinity k. And X is a topological space if k is 0. CK manifold if k is at least 1. And I was saying that a map from X to Y is a C0 embedding if it's a homeomorphism onto its image, and a CK embedding for K at least 1 if the image is a CK manifold and the map is a CK diffeomorphism onto its image. And now this is where I just was. So a class of flows C is CK universal for another such class D, and I suppose you can see my notes. Okay. Um, a class of flows C is CK universal for another such class D if any flow in D can be equivariantly CK embedded into some other flow in C, meaning there's a CK embedding H from X into Y, such that for all time, if you flow uh, in X and then embed, that's the same as embedding and then flowing. So in other words, this is a CK conjugacy onto the image of H. Um, and this is a natural notion because conceptually, such an embedding just CK identifies the system X, phi, and D with the psi invariant subset given by the image of H in Y. And this is a submanifold of K is at least one. So in other words, a class of flow C is CK universal for another class D if any dynamical system in D can be realized as just an invariant subset or submanifold of some flow in C up to CK diffeomorphism or homeomorphism. So the CK universality problem, and here I'm giving definitions essentially identical, but I have this CK generalization of generalizing definitions of Terence Tao, Robert Cardona, and Francesco Presas, and Gonzalez Prieto, Miranda, and Peralta Salas. And so this problem is given some class of flows, some class of CK flows C, what is the largest class of flows D such that C is CK universal for D? And for example, Tao solved the C infinity universality problem in 2017 for the class of so-called potential well systems. So these are flows generated by ODEs and Riemannian manifolds of the form x double dot equals minus gradient of some potential of x. Um, but in my talk, I'm not going to be talking about the potential well systems. From here on, I'm going to be talking about the CK universality problem, where C is the set of all linear dynamical systems on Euclidean spaces. So equivalently, this is the CK global universe or global linearizability problem, which asks the question, what class D of flows are globally linearizable by CK embeddings? And if you're asking, why should you care about this? Well, I'd argue that linear dynamical systems are the simplest ones, and therefore this is the most natural universality question to ask. Over in the applied world, there's this resurgence of Koopman operator theory. People are interested in using it to actually learn things about unknown nonlinear dynamical systems where you have, let's say, trajectory or observations of trajectories or just some observing some scalar valued functions. And these algorithms implicitly assume global linearizability. And so the dynamical systems better be globally linearizable if these algorithms can have any hope of succeeding. And in back into a more mathematical realm, this global linearizability question can be viewed as a natural following work of Mostow and Pillay. And the question is just to what extent does the Mostow-Pillay equivariant embedding theorem for group actions of compact groups or proper group actions, when does it extend to CK group actions of R? Because the group actions of R in dynamical systems theory are essentially never proper in interesting cases. Um, so briefly, some sufficient conditions for global linearizability. Well, first of all, locally, uh, classical results. I'm only stating for simplicity on this slide the C0 versions, uh, but near a hyperbolic equilibrium or periodic orbit for a C1 flow, Hartman-Grobman theorem and the nonlinear flow K normal form theorem tell you that you can always find linearizing coordinates. The linearizing embedding, it's a homeomorphism for Hartman-Grobman. For flow K, it's already dimension increasing. Um, But for the global case, if you now restrict to stable equilibria and periodic orbits, so some lesser known results is if you have a globally exponentially stable, so hyperbolic and asymptotically stable equilibrium or periodic orbit, then actually on the entire basin of attraction, I guess, which is the entire state space, if I say globally, um, uh, uh, a globally linearizing C0 embedding always exists. But actually, you don't even need hyperbolicity for the case of equilibria. If you have a globally asymptotically stable equilibrium, not necessarily hyperbolic, there is always a globally linearizing change of coordinates. And the proof of that result, I'll just mention, relies on various results related to the Poincare conjecture. So the previous talk mentioned Smale, Smale's H-cobordism theorem, Perelman's results, Friedman's results. And the idea is you use a Lyapunov function to find a hypersurface transversely intersecting all non-equilibrium trajectories exactly once, and then use these Poincare conjecture type results to identify that hypersurface with a sphere in a Euclidean space, and then you use the flow to just extend this identification to non-equilibrium trajectories, and then you use continuity to extend to the equilibrium. Um, and so, as I mentioned, uh, these embeddings are dimension increasing for periodic orbits, but dimension preserving for equilibria, so homeomorphisms in that case. And of course, in non-globally attracting cases, you can always just restrict to the basin of attraction to apply these results. But about this subject of equilibria, one interesting thing about allowing dimension increasing embeddings rather than the classical dimension preserving homeomorphisms and diffeomorphisms, well, already we need these for the Floquet normal form. But various classical impossibilities, such as the existence of linearizing homeomorphisms in the presence of multiple isolated equilibria, so that cannot happen if you cannot find a linearizing homeomorphism in that case, but they actually become possible for dimension increasing linearizing embeddings. Um, so, for example, a theorem proved in a preprint with my collaborator Philip Erthun is that for any uh, n greater than one, there is a C infinity flow on Rn, so R2 or greater, with your favorite finite number of isolated equilibria that is linearizable by a C infinity embedding. And in fact, if you work hard enough, the embedding can be taken of the form h of x equals x comma g of x. In other words, these are graph-like embeddings. They're graphs of some function g. Uh, and embeddings of this special form are nice because if you're interested in practical things like this applied Koopman stuff, well, you want to be able to invert your embedding. And even if you have an invertible nonlinear map, in practice, inverting it can be very hard, invertible onto its image. And but in this case, the inverse is just given by project onto the first however many coordinates. So these practically useful embeddings were studied in very classical work in control theory by Claude Fliess and Isidori, and recently by Balabas and Chen. And I just want to show you an example. From the same preprint, um, we have a pretty concrete example. It's not graph-like because I need more dimensions to show you that. But here's an example of a very simple, if I remember correctly, actually a polynomial system on R2. It might actually be quadratic. It is Hamiltonian, and it has two isolated equilibria here and here, and you can actually fold it over into, R3 and stick it inside a linear dynamical system, just x dot equals ax on R3, where there's a line of equilibria, the z-axis, going through these two equilibria here. Um, So those were some sufficient conditions for global linearizability and an illustration of some funny things that can happen. As far as necessary conditions, though, when can these linearizing embeddings not exist? So again, just talking about the C0 case, but that will imply the CK case on this slide. So if there is a countable number uh, of more than one of omega limit sets, but at most a countable number, such as isolated equilibria. And if you add the assumption that all forward trajectories are precompact, then Liu, Oze, and Sontag proved that a linearizing C0 embedding cannot exist. And similarly, but alternatively, if you have more than one non-empty compact attractor, or more generally, a single non-empty, non-global compact attractor, then you also cannot have such an embedding. And I'll just briefly mention that when I say attractor, that's my shorthand in this talk for asymptotically stable invariant set. So attractor in the sense of Conley. Um, and So I wanted to state some necessary and sufficient conditions for existence of a linearizing embedding. And so to do so, I'll just make the blanket assumption that all state spaces are connected to avoid a lot of trivial extra details in statements. And I won't be able to provide necessary and sufficient conditions in general, but I will be able to provide them for linearizability by a CK embedding if there is at least one non-empty compact attractor. And that actually includes the case of a compact state space, which is trivially a compact attractor. So I'll state that case separately as well. So in other words, I'll describe a solution to the CK universality problem, where C is linear dynamical systems on Euclidean spaces. But under the additional constraint that D, so I'm looking for all the flows D that embed in linear flows, I'm going to constrain it to belong to some class E, where E is all flows having at least one non-empty compact attractor. So under this constraint, uh, we can solve the problem. Uh, so as I mentioned on the previous slide, since if there is a non-empty, non-global compact attractor, then X phi is not linearizable by a C0 embedding, to obtain the solution just mentioned, it remains to consider the case of a global compact attractor, again, including the case of a compact state space. And I'll just mention again that if you have a local attractor, the results can still be applied after restricting to the Bayesian of attraction. So in order to state the results precisely, I need to say some things about tori and torus actions. So I'm going to be thinking about the M torus as just a Lie group isomorphic to R mod Z to the M. So just vectors with M real entries, but addition defined element-wise modulo 1. And a torus action, just a special case of a group action where the group is a torus on a space S, is just a map theta from the torus cross S into S, satisfying this same kind of property that flows satisfy, the group property. So theta 0 is the identity, and theta tau 1 plus tau 2 is the same as doing theta tau 2 followed by theta tau 1. The third definition here is the only slightly non-standard one that we introduced, but it's almost a standard one. So we say that a one-parameter subgroup of a torus action is a flow phi, which is of the form phi t is theta omega t. Again, this is mod 1 upstairs for some omega in Rm. And the final definition is a bit technical, but it is a totally standard one. We say that theta has finite orbit types or finitely many orbit types if there are only finitely many subgroups H that are the stabilizer of some X and S, where the stabilizer of a point X is just all the torus elements that fix X under the torus action. So with these definitions, I can at least state the special case of the solution for compact state spaces. So I'll split the solution into a CK statement and a C0 statement. So for the case that K is at least one, let phi be any CK flow on a compact CK manifold, X, then X phi is linearizable by a CK embedding if and only if phi is a one parameter subgroup of some CK torus action. And then the C0 theorem is almost the same, except now we can let X be a pretty general space, but ultimately it will have to be homeomorphic to a subspace of a manifold. So I guess not that general. And let phi be any continuous flow on X, then X phi is linearizable by a C0 embedding if and only if the same thing, phi is a one parameter subgroup of a C0 torus action, but now we have to add this assumption with finite orbit types, and that assumption is automatic in the CK case, so it didn't appear up here. And of course, if X is non-compact, you can still apply these results to compact invariant sets to, in particular, get necessary conditions for existence of linearizing embeddings. So I want to briefly mention some corollaries of the CK result. So I won't have time to explain the proof, but basically the CK theorem plus Bachner's linearization theorem from Lie group theory uh, tell you pretty immediately that uh, if you have a C1 flow that can be linearized by a C1 embedding, and if that flow has at least one isolated equilibrium, then the state space actually has to be even dimensional, and the Hopf index of the generating vector field at any isolated equilibrium has to be +1. Well, that proposition immediately gives you the corollary that if X is odd dimensional and there's at least one isolated equilibrium, then the flow is not linearizable by a C1 embedding. And the proposition also tells you, for example, that if you have a C1 flow with only finitely many equilibria, and if it's linearizable by a C1 embedding, uh, then using the proposition and also the Poincare-Hopf theorem, the Euler characteristic of the state space is just the total number of equilibria with no signs in the count, no at all. And in particular, it's got to be non-negative. Um, so, uh, um, so the Euler characteristic, if you have a triangulation, it's just this alternating uh, sum, vertices minus edges plus faces and so on. And for example, if you have flows on this pretzel down here or this three-way pretzel down here, if there's an isolated equilibrium, then the flow is not linearizable by a smooth embedding because they have negative Euler characteristic. I should say if all these if all the equilibria are isolated. So quick example of the C0 case. These are all flows generated by circle actions. So the previous result immediately implies uh, that they're linearizable by C0 embeddings. And in fact, the C infinity theorem tells us that the third case is linearizable by a C infinity embedding. Now, to state the general result, I need this notion of asymptotic phase. So if you have a global compact attractor A for a flow, an asymptotic phase map is just a retraction from the state space to A that commutes with the flow. And it readily follows that if you have a continuous asymptotic phase map, then the trajectory of any point in some fiber up here in yellow, the asymptotic phase map, asymptotically coalesces with the trajectory of its buddy, the intersection of the fiber with the attractor. So you say that X is asymptotically in phase with P of X. And so the main theorem in the general case for the C0 case is if you have a reasonable topological space, in particular locally compact, and you have a C0 flow on the space with a global attractor A, then that flow is linearizable by a C0 embedding if and only if the following two conditions hold. One is that there has to be continuous asymptotic phase, and two is that the flow on the attractor has to be a one parameter subgroup of a C0 torus action with finite orbit types. And moreover, if you wanted to only consider injective C0 maps rather than C0 embeddings, well, then any linearizing such map is automatically proper, hence also a topological embedding. So I think I might be out of time. Maybe I'll just skip the CK case and say that the dynamics on the basin of any asymptotically stable periodic orbit is linearizable by a C0 embedding if and only if there's C0 asymptotic phase, whether or not the periodic orbit's hyperbolic, and this is just a consequence of the preceding result. So I'll skip the CK case. Um, and I guess maybe I'll just mention that there are some interesting connections to normal hyperbolicity in the CK case. And I'd like to thank you for your attention. And I have references if anyone would like to see them. And I'll stop there.
Well, thank you for a very interesting talk. I'm closing the recording right now. So the recording is stopped. And I see that there are already some questions. So Rodrigo has raised his hand.
Yes, it's just